Hello, and welcome back to Stat 2050 at the University of Wyoming, online, and man, we're having a great time. It's a new week, so that means some new stuff. Today we're going to be talking about, at least in this video, in this series of videos, I'll say, we'll be talking about the normal distribution, standard deviation, the central limit theorem, and z-scores. Okay, so we're a bit familiar with the normal distribution by now, right? So that is just the bell shape and symmetric distribution. But we're able to define some things about it, some characteristics about it, a little bit more in this video. So before we actually get into it, I want to give the album of the week. Here it is. It's Sound and Color by Alabama Shakes. Literally every song on this album is just an absolute hitter. So I check it out. And just look how cool they are. Look. That's the Alabama Shakes, though. Brittany Howard, right there, second to the left, is the lead singer, but she also plays guitar, too, and she's really good. She has a bunch of solo stuff, too, that you should check out once you're done checking out Alabama Shakes. If you haven't heard of them, check them out. If you have, good for you. Okay, so let's get into it now that we have the album of the week. All right, so the normal distribution. Okay, so we're familiar with it. We are familiar. It looks something like this, right? So if I draw just a number line, it could be any numbers, it doesn't matter, but it looks like this, right? Actually, I'll do a different color. Looks like this, right? Symmetric and bell shape. And sort of when we're working with the normal distribution, we're always sort of focused on the idea that we're measuring something continuous, right? So kind of that decimal sort of scenario rather than like whole numbers. Now we still can draw bins, right? We still can draw bins, so it would look like this, right? Roughly, right? Roughly. But I'll quickly get the rest of them in there. But we don't really concern ourselves with the bins much anymore. We really only care about that smooth line. Oops, I just erased everything. We just really only care about that smooth line that kind of represents the overall shape of the data, right? The overall shape. And it looks like this, right? Symmetric, nice and symmetric. This is the halfway point. Each end, ideally, is even, right? So that's what that sort of symmetric means. Bell-shaped, just giving us something realistic to compare it to. And then we're working with this continuous data, okay? But a bit more about the normal distribution is that it can vary in location, right? So maybe instead of being here in the middle, it can also be, over here. So it's the same shape, just the overall location of it has changed. And it can also vary in spread, where maybe a normal distribution with a lot of spread would look like this, whereas a normal distribution with less spread would look a bit narrower, and it would look like this, maybe, right? I'm not an artist, but you kind of get the idea, right? That we can have these two different things that change its overall sort of shape and location, okay, or its spread and location, we'll say. All right, so that might not make the most intuitive sense. So let me give you an example to kind of lead into this idea of standard deviation. Okay, so let's say that we're designing a town or we're designing a city, like in Animal Crossing, if you've played that game. You start off with Town Hall, right? You start off with Town Hall, and that's sort of like the center of your town. That's where people kind of congregate. It's where people often want to live close to, right? Is Town Hall, maybe. Okay, so let's say that we start off with 4 houses. 1, 2, 3, 4. Okay, so Town Hall is right here in the middle, TH for Town Hall. We have a bunch of different houses around it. All right. And then somebody comes up to us and asks, well, where's the center of town? Well, the center of town is right here at Town Hall. So this is our center. All right. And then they ask, well, how spread out is the town? Well, then what we would do is we would just calculate the average distance away from the house, away from each house to Town Hall. So it looks something like that, right? It looks something like this. All right, where each one of these lines represents some distance. And then we would be able to say, well, on average, the average distance from Town Hall is fill in the blank, whatever. Okay, So that's fine. So let me erase this, and let me erase these lines here. Let's say that that person then decides to move in, but they maybe don't want to be that close to town hall. They decide to live way up here. All right, now someone else comes up to you and asks, what's the average distance from town hall? Okay, what's the average distance from the center of town? Well, then you would do the same thing, right? Measure each one of these, measure the distance from each house to town hall, but then you get to this guy, right? We have to go way far over and way far over, okay? And then that's going to change your average distance by a little bit, but it will make it slightly larger than it was before, okay? So that's this kind of idea of spread, how you can have, a house that shows up way out here, way out in the outskirts that can kind of affect the overall spread of the city, right? So what if we had a town that was, less spread out? So it was very clumped, we'll say. Then it would look something like this. We have a bunch of houses on top of each other. Put some up here too, right? Someone then asks you, well, how spread out is town? You've got a pretty good idea that when you measure the average distance, everything here is pretty clumped together. There's not a lot of spread, right? There's not a lot of spread away from town hall. Okay, so town hall is still sort of our center. Okay, on the other hand, if we were to get rid of all of these houses, rearrange them, and put them way out here, right? Okay, now the distance between each house and town hall is much farther away. And we could say then that the average distance away from town hall is very large, right? It's very large. And that's going to make our city look a little bit different, right? Okay, so our center of town can be anywhere. Again, to the town hall, we can put town hall anywhere, but that's our reference point. Is this town hall. Well, the same, the same can be said for distributions. Okay, I'll just do it on this page. The same can be said, actually I'll do it here. The same can be said for distributions, okay? So our center, we have three different measures of center, okay? We have the mean, the median, and the mode, recall from last week, all right? So that's fine, but oftentimes in statistics, we really only care about the mean. The mean is what a lot of tests are based on. A lot of formulas are based around the mean. The mean tells us quite a bit of information. So that is what we'll be sort of worried about just for now. Okay. So our center of our distribution, of our normal distribution, big key word here is that we're working with our normal distribution. So I'll draw it like so. All right. Let me be a little bit. There we go. Okay. All right. So our center of our distribution is right here at the very tippy top, right? At the very tippy top. We know that represents the mode and the median too. And in our normal distribution, all of those values become right about the same, right? They're approximately the same, but since we're only worried about the mean, that's all we're going to care about, okay? And depending on the context in which we're working, this center here can either be represented as, and let me actually write it a little bit better because this is important. All right. Can be represented as mu or as x bar. Okay, so let me come down here. Mu, let me show you the formula. Let me show you the formula for mu. Hopefully it looks familiar. Look at that. All that is the mean. All that is the mean. But since we have these two different symbols, that means that we can use them in slightly different contexts. In this case, mu is just the population mean. Okay, so the location, our location parameter here is just the population mean. Or if we're working with a sample, and I'll do it in a different color here too, because oftentimes we do work in samples. Instead of mu, we'll use this x bar. We use this x bar. So it's just an x with a bar over it. But the formula is still the same thing. All right, the formula is still the same thing. So this is our sample mean. All right. And so both of these are our location. If we're being very specific, our location parameter. So it just tells us where the center of the data are, just like town hall was our center of town, right? Okay, so hopefully go ahead and take a screenshot, or if you're writing this down, pause the video, because I'm going to move on to the other idea of spread. Okay, so actually, do I have? Oh yeah, I do. I'll just leave it so you can look at it whenever. So anyway, we'll come down here, draw this. So our distribution, a normal distribution looks like this. All right, we're with a center of mu or x bar, depending on what we're working in. It kind of looks like an M. Let me fix that. There we go. Okay, so depending on what we're working in, and since this is new for us, I'll write it off to the side. So it could be either. Because when I had it down here, it looked like it was being divided, and it's not. Okay, so mu or x bar, depending on the context we're in. This represents our center. This represents our center of the data. All right. Then we're also able to say, well, how spread out is the data? Sorry, how spread out are the data? It's plural, whatever. How spread out are the data? Well, we're able to define that by just saying, well, if we were to take, we have a bunch of different points on here, and let me do it in a color so we can see. We have a bunch of points on here that show up, where a lot of the points in our data set show up right here, but some of them are out here and out here. Less of them. Most of them are clumped up around here, but we do still have some in the outskirts, right? We still have some in the outskirts, all right? So all we need to do is just calculate the distance between each one of those values and the mean, and we'll be able to take an average of those distances and be able to define the overall spread of our distribution, all right? So that looks like something like this, right? So it's the average distance away from each point, the average distance that each point is away from the mean, okay? And we've got some special symbols for that too. So let me go back here, blue and green. All right. So if we're working in the population world, which often we're not, but still sometimes it might be applicable, we'll use this, good Lord, we'll use this Greek symbol, sigma, okay? And sigma just represents the population standard deviation. Deviation. Okay? So the overall, sort of the average spread of our population distribution. All right? We have the same thing on the other end. Same thing, but we just use S instead. And that's going to be our sample standard deviation. And standard deviation is just that fancy word for more or less kind of the average distance that the points are away from the mean. All right. So I did not write out the formulas for these for a reason, because I have them here on the next page. And they're also, well, they're not too complicated. They look more complicated than they actually are, but they're right here, okay? And I've got the population mean and the sample mean formulas down there too. They're identical. They're the same process, right? Sum up all the things, divide by how many things you've got. I just wanted to show here that it's mu and x bar, depending on the context. And it's also the same situation up here. We have the population standard deviation and the sample standard deviation. Okay, so instead of trying to, just leave you at it with these formulas, I'd like to do an example, okay? And so one thing to note, well, actually, I'll just note it in the next video. Go take a break, go sip on some coffee, and I'll see you here in just a second.